Hello everyone. I think can you people hear me?
Yes.
Okay, thank you. I think we should wait for some time and after that we will start. Okay, I think we will start right now. I am sharing my screen. Okay. Just a minute. Okay. Welcome everyone. My name is Papia and I am the teaching assistant, PMRF Nptel teaching assistant for the course of nuclear and particle physics. Today is basically the assignment 2 and we will talk about assignment 2 which is for week 2 session and okay, let's start about this. The first question will be like that. The first question is what is the expected spin value of the ground state of the nucleus N715 within the nuclear shell model, and the four options will be 0, half, 1 and 3/2. So before going to the main answer of this question, I should talk about something which is just a minute. Which is known as a shell model. What is basically the shell model? So here basically I would write something for explaining. Okay. Okay, so what is basically cell model is? So cell model is basically nothing but a model which will describe about the nuclear properties. Okay, so that means like here I will describe about some of the models which can explain the neutron properties. Neutron properties, neutron as well as proton properties, as a whole nucleus properties you can say. So here basically there are so many models which can explain most of the properties of nucleus. Like first of all I can tell about that liquid drop model. In the previous lecture we already know about what is liquid drop model, and there we have used one main example, one main expression for the liquid drop model, which is semi-empirical mass formula. Just a minute. So the first one is the liquid drum model, which we already know about that in the previous lecture. So right now we are going to tell about one of the most significant and most efficient model, which is cell model. So cell model, before going to the cell model details, I would like to say why we need cell model, because the liquid drum model was the one of the most successful model, but why we need a liquid cell model instead of liquid drum model? There are so many drawbacks of liquid drum model. Like in that liquid drum model, as we can see that we suppose that our nucleus as a liquid drop, and there are the nucleons inside that liquid drop. The molecules are the nucleons. So basically the problem with the liquid drum model is like that liquid drum model liquid drum model assumes collectively as a model, like the nucleus, inside that nucleus all the nucleons are same. It is assumed by liquid drum model, but basically neutron and proton are obviously not same, and they behaves differently. And also in that low energy state, why the low energy states are widely separated, that is also unexplained by liquid drum model. So that's why we are talking about something more than liquid drum model, which is known as cell model. And also the magic number, I will tell what is magic number basically. So the magic number, magic nucleus also can't explain by the liquid drum model, so we should go beyond liquid drum model, which is known as cell model. Okay, so what is basically the cell model is? Cell model is nothing but a very much equivalent to our electronic cell model. So in that electronic cell model, each and every electron, we can assume that each and every electron is stepped in a cell. Like if I have a cell, like here there are so many energy levels are there. In that energy levels, electrons are staying here. So that means just as the very similar of that electron cell model, we can say that nucleus is also placed, nucleons are placed in the cell as very similar to the electronic cell model. So here the cell model is basically for neutron and proton. It can explain most of the properties of nucleus. So like first of all, it can it can describe magic number. It can describe magic number. It can also describe that whatever I have told right now, that what is the drawback coming from the liquid drum model, what that is that low energy states are widely separated, why it is like that. So this can also be explained by cell model. And also we can explain why there are so many isotopes in our why there are so many isotopes in our nature with the specific some numbers, neutron and proton, which is called as magic number. This type of, and why in that there are specific proton, there are specific nucleus which has a very large number of binding energy. Why it is like that? We can explain all the properties, all these things with the help of cell model. So in that cell model, basically what happens, in that cell model, the neutron and proton, that means N and Z, as we already mentioned in the previous lecture, what is N and what is Z. So in that is N is basically the neutron number and Z is proton number. So in that cell model, neutron as well as proton, it can be separate, it can be distributed among the different energy levels. Like different energy level means it is like 1s and then 1p. In that 1p, due to the spin orbit influence, the two portion will be there, or 1p 3/2 and 1p half. I can't go to the exact details about all the things, because obviously due to the time constraint, but I am telling the basic things of a cell model. So here 1s, in that 1s half there will be 2 nucleons, because obviously due to the Pauli exclusion principle there should not be only there should not be any other 2 fermion which have the same quantum numbers. So in that 1 is a half 2 nucleon will be there, and in that 1p 3 by 2 means 4 particle will be there, and for that 1p half 2 will be there. So like this, so that means as in our example what it is given here, the nitrogen. For that nitrogen it is given that nitrogen 7 and 15. So that means for nitrogen 7 and 15 we can write that Z equals to 7 and N equals to 8. 15 minus 7, that means 8. Okay, so that means Z equals to 7 and N equals to 8. That means as a whole 15 nucleons is there. But if I consider neutron and proton are different, so that means 7 proton is there and 8 neutrons are there. So like 8 neutron is there. So if 8 neutron is there, that means if I write the cell model structure here, the cell model structure can be written as 1 is half 2. Here why it is 2? 2 is basically the number of nucleons placed in that cell, in that energy level. So 2 is nothing but the 2j plus 1. So j is what? J here for 1 is half, j is half, so that means 2 into half plus 1. So as a whole 2. So that means for 1 is half, this energy state to maximum 2 nucleon will be there. So that means 1 is half 2. It is a standard notation for the cell model structure, and for that then 1 p 3 by 2 4. Why 4 is there? Because 3 by 2 into 2 plus 1. Okay, so 3 by 2 into 2 plus 1, that means 4 will be there, and then 1 p half 2. Obviously if there is half, then half into 2 plus 1, that means 2. So this type of configuration will be there. So as now we will write the neutron configuration as well as the proton configuration. So what will be the neutron configuration? The neutron configuration will be like that. Oh sorry, yeah, 1 is half 2, 1p 3 by 2 4, and 1p half 1 for, see, like here in that notation 2 is there, 4 is there, so as a whole it is 6. And if 1p 2 will be there, so that means it will be basically nothing but the neutron structure, neutron cell model structure. But if it is n equals to 2, that means it's a half full field. I mean, like for p there is only 2 is there, only that maximum number can be accessible in that state will be 2. So that means if for the neutron case it is totally half full, a full field, it is a typo, it will be half field. So the full field. So that means for neutrons there is no valence electron, valence neutron or nucleon, whatever you can say that. But for the proton the 7 is there, but for 7 means like 1p half 1 is there. So as 1 is not a full field configuration, so that all the properties, all the nucleus property can be determined by that valence nucleon. So the orbital configuration for the ground state is this one for proton. We are not considering here the neutron configuration because neutron configuration is half filled here, full filled here, so that's why. Okay, here it is. Okay. So that's why we are only considering about the proton configuration, the orbital configuration for ground. The proton configuration, proton's orbital configuration for ground state is like that: 1 is half, 2 will be there, then 1 p 3 by 2, 4 will be there, and the other one is 1 p half 1 is there. So in that question they were just asking that what will be the value of the spin of the ground state of nitrogen 715. As I already told that the all the nucleons or nucleus properties is determined by the valence nucleons. So for that in that case nitrogen 715, the valence electron is valence nucleon is basically nothing but the last nucleon, last proton. So the spin is obviously a nucleus property, so that means spin can be determined by only that last one. So what is the last one configuration? I can write here the last one configuration is 1 p half 1. Okay, so someone has come. Okay, so that means the spin of that orbital ground state will be, spin is basically that nothing but half, which is given here. So that means the answer of that question will be B, because in that question the option number B is half. So if one can ask that what is the expected spin value of the ground state of nucleus nitrogen 715 within the nuclear cell model, we have to find that which one gives us the valence nucleon. So if we can find that which one gives us the valence nucleon property or which one is the valence nucleon, then according, the corresponding orbital configuration of that valence electron, we can say that what is the value of J, what is the value of L, etc. That means spin angular momentum what will be, orbital angular momentum what will be, we can say like that. So this is about the first question. If anyone have any question, then you can just ask me. I am not going details about that cell model, because in that cell model there are so many things, and I will also tell some more about cell model when we will go question by question. But for that right now, like for the question number 1, there is only the known thing is that the valence nucleon will be the main responsible for giving any neutrino properties, nucleus properties. So as spin is obviously a nucleus property, so that means we can have the knowledge about the spin of that nucleus from the valence nucleon. So I think there is no question, so that means we will go to the next question. In the next question, the question is what is the expected parity of the ground state of the nucleus silicon 1429 in cell model. So obviously the parity is also a property of a nucleus, so that means as in that cell model the very similar question about just like the first one. So at first we have to find that what will be the valence nucleon. Okay, so what will be the valence nucleon here for silicon 1429? So let us write here silicon 1429. So for that Z equals to 14 and N equals to 29 minus 14. So that means it will be 15. So as I already told you that 14 will not give any valence neutron, only nucleon, only the main responsible here for that neutrino properties, nucleus properties will be neutron 15. So 15th number nucleon will give the neutrino property, nucleus property. Wrong. So that means for silicon number of neutrons is 15 and number of protons is 14. So as a number of protons is not a valence nucleon, so that means the main responsible for our parity or whatever spin or whatever you can say about the nucleus property is due to that 15th neutron. So therefore the orbital configuration for ground state according to the cell model we can write like that: 1s half 2, 1p 3 by 2 4, 1p half 2, 1d 5 by 2 6. Now coming to the 2s half. In the 2s half part, this is 1. So as a whole, if I calculate that 2 plus 4 plus 2 plus 6 plus 1, so that means what it will be: 4 6 6 12 14 15. So it is a 15 configuration. So coming to the last one, this is the responsible for that nucleus property. So in that last one, what is the last one? I can write here. The last one is that 2s half 1. So basically in that state, what is the value of j, what is the value of s, and what is the value of l something. So for a state, obviously for a state we can have that l equals to 0. As we all know that, okay, I have to write here something, l and that specification. Okay, so for l equals to 0, 1, 2, 3, 4, 5, 6 and all the things, the specification will be S, P, D, F, A, G, H, I and so on. So that means if L equals to 0, the specification will be S state. So that means L equals to 0 in that last, in that valence nucleon. So that means if L equals to 0, the parity is obviously minus 1 to the power L. So that means minus 1 to the power 0, which is nothing but a positive value. So that means it's a even parity. So in that question, what was asking here, the question was basically what is the expected parity of the ground state of the nucleus silicon 1429 in cell model. So we already wrote down what will be the ground state of configuration of that silicon 1429 nucleus, and after that we calculate that, we just at first find out what is the valence nucleon, and after finding that valence nucleon we have the value of S. Here we have the value of L here, and by putting the value of L here, that is 0 here, minus 1 to the power 0, that means positive. So that we can write that the expected parity of the ground state will be even, because it's a positive value. So this is about the second question, and the answer will be even, that means first one. So I think there is no question till now. You people can ask me question if there is any problem. Okay. So now coming to the third question. The third question is a little bit elaborative way I can discuss, or it's a little bit different, not difficult, not that much difficult. Okay. So the question is within the nuclear cell mode, it should be model. Okay, whatever. Spin and parity of the first two excited states of magnesium 1225 are, what will be the spin and parity of the first two excited state of magnesium 1225? So this is the question. So as we already know, and I told you so much time that we have to write at first the cell model configuration, and after that we have to find the valence nucleon, which can give us the spin and parity knowledge of that nucleus. So coming to the portion which I need. Here it is given that magnesium 1225. So that means Z equals to 12 and N equals to, what will be the N? 13. Okay. So 12 cannot give any type of contribution in the cell model neutrino property calculation. N equals to 13 will give. So let's start with the n equal to 13 orbital configuration which comes from the cell model. So cell model which will give 1 is half, 2, 1 p 3 by 2, 4, 1 p half, 2, and see how many it is already there, 2, 4, that means 6, and 2, that means 8 is there already. So we need extra 5, so that means 1 d 5 by 2, 5. This is the ground state configuration of magnesium 1215. Okay. So this is the configuration for the n equals to 13 through the cell model configuration. So basically this is the ground state contribution, ground state configuration. But here in that question they were just asking that what will be the first two excited state configuration and then what will be the spin and parity. So we have to go beyond ground state, we have to go the first excited state and the second excited state. So I would like to draw some energy diagram like here. Okay, I am only taking about 1 p 3 by 2. And I am only talking about 1 p 3 by 2, 1 p half, 1 d 5 by 2, then 2 s half, and then 1 d 3 by 2. Okay, so in that 1 p 3 by 2, 4 will be there, 4 nucleons will be there. So that means we can write here something 1 2 3 4, and for 1 p half 2 will be there, so I am writing like that. And for 1 p 1 d 5 by 2, in that ground state mentioning what is the value 5. In that ground state configuration the 5, sorry, 1 2 3 4 5 nucleon will be there, and there is no nucleon in that 2s half and 1 d 3 by 2 state. So this is the configuration for ground state. Ground state I am just mentioning here with 0. Okay, so now coming to the first excited state. What will be the first excited state energy contribution? So as we can see here, these two has no problem, so that means we are neglecting these two term right now here. So in that first excited state, what will be the configuration? In that first excited state, let me write 3 energy state. So the first one is 1 d 5 by 2, then 2 s half, and then 1 d 3 by 2. Okay, so here in that ground state, in the 1 d 5 by 2, there was 5 particles, 5 nucleons. So but the 5 nucleons is not stable, because 5 nucleons means like due to the Pauli exclusion principle, what will be the value of that angular momentum? This up down, this up down, and let's say it is a up. So that means it's not a stable state. So if in the ground state, what in the first excited state, what will be if I just give some energy to that configuration, then what will be the last one, which is the single one, it is not paired. That unpaired nucleon can go to the higher energy level. So that means what will be the expression for that first excited state? 1 2 3 4 will be there, and the latest one, that means this one will be here. Okay, this is the first excited state. So but here there is nothing, 1 d 3 by 2, there is no particle, there is no nucleon, because obviously 5 is already covered here. So this is the first excited state configuration. Now come to the second excited state configuration. Second excited state means we are giving more energy than first excited state. Then what will be the configuration? So here I am writing the same thing. Okay. Okay, so coming to the second excited state. In that second excited state, I am still writing the same thing, 1d 5 by 2, then 2s half, oh sorry, and then 1d 3 by 2. There is no more space. So, okay. Then what will happen? 1, 2, 3, 4. These 4 nucleons are basically very stable and very compact in the form. So that means if we are increasing high energy here, if we are putting some energy into that first excited state also, these 4 nucleons can't, they want to go to that higher level. They are here fixed because they are obviously paired here, because paired nucleons are very much stable. So that means they don't want to go anywhere. So, but the problem is with that, this one can go here. So that means in the second excited state, what will be the configuration? There will be no nucleon, or there will be one nucleon, and there 4 nucleons will be there. So that means this is the second excited state configuration. So I think you all understand that what will be the first as well as what will be the second excited state configuration according to the cell model. Now coming to the expression, like this is the main thing in that question, that what will be the first excited configuration and what will be the second excited configuration. So I have mentioned here that for magnesium, number of neutron, so here the number of neutrons is 13 and number of protons is 12. So that means the orbital configuration for ground state, as I already mentioned here, this is the ground state, this is the first and this is the second excitation. So in that first ground state, I can say that 1 is a half 2, 1p 3 by 2 4, 1p half 2 and 1d 5 by 2 5, as I already written here in this configuration. So coming to the first excited state. In that first excited state, as whatever I have written here in that configuration, then what will be the configuration for 1? For the 1, the configuration will be like that. The first 3 will be very similar. The only difference will be 1d 5 by 2. Here the 4 will be there, and the second one will be 2s half and 1, which I already written here. Okay, so the first excited state corresponds to that configuration. Now coming to the spin and parity part. As I already find that what will be the valence nucleon here, then I can also calculate what will be the spin as well as what will be the parity of that configuration. So the first excited state has the spin like half, because 2s half is there. And for L equal to 0 for A state, as it is the 2s half, so that means S is there, S state means L equals to 0. So that means the parity will be minus 1 to the power 0, which is even parity. So the first excited state corresponds to the spin half and parity is even. I think all you can understand what is the spin and parity for first excited state. And for the second excited state, in the second excited state, as I already drawn here, the second excited state, what will be the one? The second excited state will be, the first 3 will be same, but the last one is 1d 5 by 2 4, and instead of 2s half, there will be 1d 3 by 2 1. Okay, so that means the valence nucleon is 1d 3 by 2, and for 1d 3 by 2, L equals to 2, because D is there, S P D, that means 0 1 2, so L equals to 2, and the spin will be 3 by 2. So that means the spin will be 3 by 2 and L equals to 2 for D state, that means minus 1 to the power 2, which is even number. So for first excited state, the parity will be positive with half spin, and the second excited state parity will be positive with 3 by 2 state. Okay, I think it's clear to all. So that means the option will be B, The option was, what is the option B? Yeah, the B option is half even, 3 by 2 even. Like first x state half even, and for second x state 3 by 2 even. I think it is understandable by all of you. Okay, if there is no if there is no other question, then we should go for the fourth question. The fourth question is like, consider the classical case of a particle of mass 1 into 10 to the power minus 30 kg and charge 1.6 into 10 to the power minus 19 coulomb, which is moving in a circle with angular momentum 2 into 10 to the power minus 34 joule into second. Then the question is, the magnetic dipole moment associated with this will be, like, what will be the value of magnetic dipole moment in that system? So the system has some, the given parameters are m, q, the charge of that particle, and angular momentum, which is nothing but m v r. Okay, so that means angular momentum is m. So these three data is given with us. And what will be the expression for magnetic dipole moment? The magnetic dipole moment can be written as mu, which is like I into A, as I already know here. So I into A means I can be written as Q by T into L into L into half. So that means Q L by T L into half, which is Q, L by T is V, and L we can write as R, whatever, and by 2. So here the configuration is like half Q V R, but we are given that M is there and MVR is there and Q is there. So we can do one thing, that half MVR Q divided by M. Okay, so that means what? Half L by M into Q. Simple. So by putting the values of M, Q and L, we can have the value of mu. So the value of mu will be like that. I have already mentioned here, half Q VR, Q into MVR by 2M, QL by 2M. So that means Q is 1.6 into 10 to the power minus 19 and 2 into 10 to the power minus 34 divided by 2 into 10 to the power minus 30. So after calculating all the things, we can have that 1.6 into 10 to the power minus 23, which is ampere to meter square in unit. So this is the expression for the magnetic dipole moment for that system. This is a very simple and trivial question for question number 4. So nothing more than that is there. So coming to the question number 5. In that question number 5, the question is like, in a scattering of electron of a nucleus, electrons of energy equals to 10 MeV are used. If these electrons are represented by the wave function, which is known as phi equals to a to the power I k z, where the position coordinate is along z cap direction, then the value of k will be what? Okay. So for that question, here, what is the given here? The given configuration is equals to 10 MeV and nothing more is there. Okay. And also one thing I have to know, that what is the value of h bar. H bar is nothing but h by 2 pi. And what will be the value of h? We have to know that. The h is something has the value I have written in that next slide. In the unit of electron volt into second. Okay. So why H is needed here, I will say little bit later. So basically what is given here, the given configuration is E, and they are saying that the electrons of energy E are used in the scattering of a nucleus, and if these electrons are represented by a wave function, that means if we are assuming that electrons are a wave nature, have a wave nature with the wave function phi equals to a to the power I k z, then what will be the value of k? K is basically nothing but the momentum. Okay, so we need to know that what will be the value of momentum of that particle, of that electron. So for that calculation, the calculation is very simple, that for the plane wave the energy momentum relation is there, as electrons are assuming as a plane wave solution, like as a wave, basically as a plane wave, because phi has the configuration a to the power I k z, which is the plane wave configuration. So the plane wave configuration has a relationship between momentum as well as energy is like, it's written here, yes, E equals to h bar square k square by 2m. Okay, and m is the mass of that electron. We all know that what is the mass of the electron, 0.511 MeV, and what is the value of h bar here? The h bar value is 6.85 into 10 to the power minus 16 in the unit of eV. Okay, so putting all the values here, like h bar square k square by 2 m and e, the expression for momentum will be k, which is nothing but root over 2 into m into e divided by h bar square, and h bar is as I already told you, h bar is h by 2 pi. Okay, so just putting all the values here, we can have the value of k. But one thing is that here when we will calculate the value of k, there should be one mistake. The mistake is what? The mistake is like the expression is telling about what will the value of momentum in the units of meter inverse. Okay, but right now we are talking about energy configuration, energy unit in MeV, and also the h bar is unit of EV. So all the things are in EV or MeV range, so we have to transfer these things in the units of meter square or meter inverse, something like that. So for that, what should I do? Like here the mass of the electron is not exactly 0.511 mega electron volt, it's a mega electron volt divided by c square, because E equals to mc square, Einstein gave us the expression. So E equals to mc square, so that means m equals to E by c square. So sorry, this one will be okay. So E square, so that means c square will be there, so that means E is 10 into 10 to the power 0.511 into 10 to the power 6, that means 0.511 MeV is there, and 0.511 MeV and 5.511 into 10 to the power 6 means it will be EV divided by c squares, and the c is nothing but 3 into 10 to the power 8 meter per second. So if I putting all the values here, then we can get the value in the unit of meter inverse, and the value will be 1.61 into 10 to the power 13 meter inverse. So the correct answer will be B, this one, 1.6 into 10 to the power 13 meter inverse. But if we don't use the C option, like C square in our calculation, then the calculation will give us a wrong value. The wrong value means like it may be given this value 4.8 into 10 to the power 21, because like 3 into 10 to the power means 1.6 into 3, so that means 4.8. It may be, or it may be given like that 5.1. I don't know, I have to check, but we always give the correct answer only if we are going to convert our all the units in the meter or meter, centimeter, something like that. So as a c equals to 3 into 10 to the power 8 meter per second, so by putting these values in our equation number 3, we can get the correct answer as 1.61 into 10 to the power 13 meter inverse. So the correct answer will be B. So
Excuse me, will you please explain the solution again?
yeah, hello.
Yeah, please explain the solution again. Irrespective of getting the answer, please explain the solution.
Oh, solution. Okay. Yes. This question is, I am going to say the question again. The question is, in the scattering of electron of a nucleus, electrons of energy equal to 10 MeV are used, and if these electrons are represented by the wave function, which is like phi equals to a to the power I k z, then what is where the positive coordinate is the z direction, then what will be the value of k is here. K is nothing but the momentum. Okay, so here the question is that what will be the what will be the value of momentum in our question. So as here electron energy is 10 MeV. Okay, so 10 MeV and the electron are represented by a plane wave function. Plane wave function has the configuration is like phi equals to a e to the power I k z, where k is the momentum and z is the direction of that particle. Like, and here the electron is there, so that means the direction of the particle is along z axis, z direction. So and the k is the momentum of that particle, momentum of the electron. So we need to know that what will be the value of momentum here. So for the plane wave, it's a very simple relation. It has a very simple relation between that energy and momentum. The relation is like E equals to h bar square k square divided by 2m. So here what is h bar? H bar is nothing but the reduced Planck constant, what is known as h by 2 pi. So here just putting the value of h bar, m and e, we all have all the values of that e, h bar and m, so that we can know that value of k here. So that means just putting the values of all the things, that means what is e, what is h bar, what is m, we can have the value of k here, which is known as the momentum of that particle. So by calculating these things, like I have here mentioned here, that 2 into 0.511 mass of the electron is 0.511 MeV by c square. So that means 2 into 0.511 into 10 to the 6 eV by c square into e means 10 into 10 to the 6 in eV, because it is in MeV. 10 MeV was there. So 10 MeV means 10 into 10 to the power 6 eV, and then in that denominator h bar square is there. H bar is 6.5 into 10 to the minus 16 as a whole square. So that means after calculating the calculations, we can have the 1.61 10 to the power 13 meter inverse. So this is a very simple expression between the energy and momentum, that E equals to h bar square k square by 2m. There is nothing more than that. Do you understand? Hello?
Please go ahead.
Okay, thank you. Yeah. So just putting that values, we can have the expression k equals to 1.61 10 to the power 13 meter inverse. Okay, now coming to the question number 6. The question number 6 gives that in an experimental measurement of the orbital angular momentum of deuterium, 10,000 samples were selected, and approximately how many of them would have measured L equals to 2 into h by 2 pi. Basically L equals to 2 into h by 2 pi means L equals to 2 h bar. Okay. So the question is like that we have 10,000 sample. Among the 10,000 sample, how many sample have L equals to 2 h bar orbital angular momentum. So for that question, I would like to say about, I would like to recall the previous week's one question, in the previous week's one question there was mentioned that what will be the value of orbital angular magnetic dipole moment of deuteron. So for that calculation, for that question we mentioned somewhere that for calculating mu, that means the magnetic dipole moment of deuteron, we need two states, and the two states is like one state with L equals to 0 and another state is L equals to 2. That L equals to 0 is 96%, like approximately 96%, and L equals to 2 is approximately 4%. It was mentioned in the previous week lecture. So if it is like that, it's the question in that question number 6 are basically telling about that how many of our 10,000 sample will have L equals to 2 state. Obviously if it has 4% contribution in one sample, so that means we can write here that 10,000 among 10,000, what will be the value, what will be the, how many of them would have L equals to 2, which is nothing but 10,000 divided by 10,000 into 4%, that means 4 divided by 100. What will be the value? The value will be 400. So that means among 10,000 sample, 400 sample will have L equals to 2 value. That means L equals to 2 h bar will be the measured orbital angular momentum. So that one I have mentioned here, that deuteron are found in two states, that is L equals to 0 with probability 96% and L equals to 2 with probability 4%. So therefore deuteron with L equals to 2 will be 10,000 into 4 by 100, that means 400 out of 10,000 samples. So that means that answer will be last one, that 400 will be there. So that means 400 samples will be in such a way that if I measure the orbital angular momentum of the systems, the output will be 2 h bar. That means L equals to 2 output will come for 400 system among 10,000 samples. Do you understand? I think it's a very simple, like if you know that L equals to 0 is in which percentage and L equals to 2 in which percentage, then you can just calculate by multiplying that number with the total sample. It's a probability thing, so that means 10,000 into 4 by 100, that means 400 is there. So these 6 questions I was wanted to know, I wanted to explain with you people. So basically as a summary I would like to say that all the first all the first 3 questions are basically coming from the cell model, which is a very important model in our nucleus understanding. So the main key point of that cell model is that at first we have to write the orbital configuration of that nucleon, and we have to find that what will be the valence nucleon for our system, and then if we can find the valence nucleon, we can have the knowledge about spin, parity, and all the nucleus properties, because the nuclear properties obviously depends on the valence nucleon, not on that compact formed nucleon. It will be only valence nucleon responsible for the nuclear properties. So these are the main features for the first 3 questions. And the fourth question, what was that? Okay, fourth question is about the magnetic moment calculation, and the fifth question is about the energy and momentum expression relation, and the sixth question is about the deuteron magnetic moment calculation. So this is as a summary I want to tell. If there is any question, you people can ask me about, among that 6 questions, if there is some problem. So if there is no such question, then we can conclude our session. Thank you all of you. Bye bye. See you next week. Bye.